Welcome to the Explainer, everyone. Today, we're completely cracking the code on KSSM Science Form 3, specifically Chapter 7. Consider this your definitive energy and power masterclass. Whether you're gearing up for a major exam, or you just want to deeply understand the invisible forces that drive literally everything in our physical world, you are exactly in the right place. We're going to break down these scientific laws to make sure you walk away with absolute clarity.
Here's our roadmap for today's session. We're going to start with work and power, move into potential and kinetic energy, tie it all together with the conservation of energy, and then lock it in with a quick chapter summary. Easy enough, right? Let's get to it.
Okay, let's dive right into this. We're starting at the absolute foundation with subtopic 7.1, Understanding Work and Power. Now, science defines work very differently than, just sitting at a desk or studying for a test. In physics, work, which we represent with a capital W, is strictly defined as the product of force, that's F, and displacement, which is S. But here is the absolutely crucial exam keyword you've got to memorize. That displacement must be in the direction of the force. The formula? Super simple. W equals F times S. And remember, the SI unit for work is the joule, represented by a capital J. So basically, 1 joule of work is done when 1 newton of force moves an object exactly 1 meter. So this brings us to a classic trap that examiners literally love to set. Imagine you're pushing a massive, heavy, completely stationary wall with all your might. You're sweating, you're exhausted. Are you actually doing any work? Well, even if you're applying a tremendous amount of force, if that wall isn't moving, your displacement is 0. And according to our formula, W equals F times 0, it doesn't matter how much energy you burn. If there's 0 displacement in the direction of the force, the work done is exactly 0 joules. You have to have movement to have work. Crazy, right? All right, let's see how this builds into our next critical concept, power. If work is all about force and distance, power adds the element of time. Power, or P, is defined as the rate of doing work. So the formula is P equals W divided by T. Work divided by time. The faster you do the work, the more power you're generating. And the SI unit here is the watt, represented by a capital W. 1 watt simply means 1 joule of work is being done every single second.
Let's ground this with a classic textbook example. Think about Kamal and Akhet. They're both carrying a 10 Newton load up the exact same flight of stairs. Now, because the force and the displacement are identical, they are doing the exact same amount of work in joules. But if Akhet runs up those stairs and takes way less time than Kamal, Akhet has a higher power output. Same work, done faster, equals more power. Makes total sense.
Now that we have work and power locked in, let's transition into our second block on the syllabus, subtopic 7.2, Potential and Kinetic Energy. First up in what I like to call our energy trio is gravitational potential energy, or GPE for short. This is energy that's stored up simply based on an object's position or height. The formula is mass times gravitational acceleration times height, or just mgh. If you lift a heavy object up high, it might not be moving, but it possesses massive stored energy potential because, well, gravity really wants to pull it back down. Let's apply this mgh formula to a real-world Malaysian example. Imagine a lift at the KLCC Mall carrying a mass of 1,500 kilograms up to a height of 30 meters. If we assume gravity is roughly 10 meters per second squared, we just multiply those 3 numbers together. 1,500 times 10 times 30. That gives us 450,000 joules. And here's the really beautiful connection. The work done by the lift's motor to pull that carriage up is perfectly equal to the gravitational potential energy it gains at the top. Our second type of stored energy is elastic potential energy, or EPE. While gravitational energy depends on height, elastic energy depends on compression or stretching. Think of pulling back a rubber band or compressing a metal spring. The formula here is 1/2 Fx, where F is the stretching force and X is the extension. The more you stretch it, the more energy is stored up, just waiting to be released. Completing our energy trio is kinetic energy, or KE. While potential energy is stored, kinetic energy is the energy of actual motion. Literally any moving object possesses it. The formula is pretty simple, 1/2 mv squared, mass times velocity squared. And notice that because velocity is squared, if you double the speed of a car, you don't just double its kinetic energy, you actually quadruple it. That's a huge takeaway. All right, we've defined the different forms of energy. Now, how do they interact with one another? Let's move to subtopic 7.3, conservation of energy, to uncover the grand rule that governs our entire universe. This brings us to the principle of conservation of energy. It states that energy cannot be created or destroyed, but can only be converted from one form to another. This means the total amount of energy in the universe is a constant, unchanging number. It simply wears different masks, shifting endlessly from potential to kinetic and back again. Pretty mind-blowing when you think about it. A really brilliant illustration of that law in action is the swing of a simple pendulum. When the bob is pulled back to its highest point and pauses for just a split second, it has maximum gravitational potential energy, but zero kinetic energy because it's not moving yet. But as it drops and swings through the lowest equilibrium point, all that stored potential energy has been converted into maximum kinetic energy. They constantly trade places, but the total energy, it remains exactly the same. So the crucial point is, how does this perfect trade-off relate to what physicists call a closed system? Well, a closed system is an idealized scenario where there are absolutely no external forces, like friction or air resistance. Because there's no friction, no energy is wasted as heat, meaning you get a 100% useful energy transformation. Of course, in our real world, a simple pendulum will eventually stop swinging because friction steals that useful energy and turns it into heat.
We're shifting into high gear now as we hit our final section, the chapter summary. Time to consolidate everything for your exams.
Here is your ultimate revision cheat sheet. Seriously, you might want to take a screenshot of this. Notice how logically it's all laid out. You've got work, W equals Fs, measured in joules. You've got power, P equals W over T, measured in watts. And then look at our three energies. Gravitational potential energy is mgh, kinetic energy is 1/2 mv squared, and elastic potential energy is 1/2 Fx. The absolute biggest takeaway here, every single type of energy, just like work, shares the exact same SI unit, the joule. Memorize this table, and you are going to easily secure those calculation marks. Before we wrap up this masterclass, I want to leave you with a bit of a provocative question. If energy is never truly destroyed, just like the conservation of energy tells us, think about all the machines, the vehicles, even your own body right now. How much of the energy we consume daily is actually doing useful work, and how much is just being lost to the environment as wasted heat due to friction? Understanding physics isn't just about passing Form 3. It's about seeing the hidden efficiency and inefficiency of the world you live in. Thanks for hanging out and learning with me today, and keep looking for the science in your everyday life.